You know, just had a long break. Woodpecker? Started, I think number two. Chapter one. Yeah, that. So I know we didn't really go home.
When you go over anything.
Yeah, it's like, is that area depending on what her shape is?
Yeah, I think it says it's into like 2 block, right?
Yeah.
So it makes it 4 more.
But the second one, since it's a pain.
So 5/4 squared.
Okay, I see that. That's what I assume. I'm just like,
It's like think of it like the circle square.
yeah,
The cross section, I should say. It's like this.
this is thing, you need the overrun, so it's like, I'm trying to find this kind of throwing.
Around 10 makers.
Yeah.
Right, I'm going for the class there. It's quite. Should I be able to do?
You probably have a quiz, right?
It's actually. I'm sure when it's supposed to open, I think I should buy this.
5:30, something like that. Is it time limit? That's the thing.
Good question. Yeah, because there's nothing on there yet, even if it, like it doesn't even exist. Yeah, check. You know how it'll be locked.
Mm-hmm.
There's just nothing on it.
So far, I'm trying to do something. Going dark set. I pretty much have his homework. But that first one though,
It's easier to use the or using the midterm equation sheet.
Mhm.
That's the one. Yeah.
Even two, there look like some tricky ones. I think that's a T. You think T2 minus T1.
I just started chapter 2.
Oh,
I don't know anything about it. Yeah.
No, that's the first one, the first chapter.
Oh, the first one. Oh, okay.
Because he says 10 Celsius. So, anybody isn't, then that's a T, which is 10 Celsius, it's just 10K. That's what I was getting from the book. It's like,
I think it's because of the scales of both. There's the both one is the other one. So because it's not an actual value, it's a difference about you can substitute this for a K. It's this kind
it's just 10K. That's what I was saying. I was looking at
I didn't know that one of those two they're the same.
the book, like, does like a brief sweep. I guess I already assumed that you know that.
Yeah.
And then it's like an example that did it. It's like, well, that's the case.
That's what we found it.
Yeah. Just like, okay.
What's up?
Is this from lecture 3 or lecture 4?
Technically it's lecture 4 because we had 1 the first week, 2 last week, so it's lecture 4.
Thank you for that. How you doing?
Pretty good.
Not gonna be looking at how that's you'll-
I know, I'm not gonna get myself sick. I'm dying of losing.
You got me wrong.
No.
I'll be.
Are you staying late, sir?
Sure.
Well, still.
Then no. I guess.
Well, yeah.
Because we need to talk about, some scheduling with you.
And who?
Our committee, we want to have like a kid, we'll put a viewpoint because you have.
No kids.
No kids. No kids. Someone else is making your part and, yeah.
Who?
One is Tristan. He's
Oh,
making
like
this
this broccoli.
He's making this broccoli, that's fine, and. If like that, so we're moving you to more of a.
That's.
Oh, they say we're Nate's sitting, that's right.
Oh. Hey, Mason, get up on
That's the file. See, he has to sit right there. He has to stare at the all the class. That's the problem. He just likes to sit there and stare. That's what this guy likes to do.
It's February. Oh, it's February. All right. Okay, you know, only because it's February.
Tonight.
It's such a.
It's start.
Oh, it's February.
It's like, it's like.
Just get up here. Only because it's saying it, just.
I have to get the thing.
Huh?
Have you told more? It's apparently better to use, they wanted a Lightroom file that was reading, so I'm like, okay, cool. It's a very prominent, like, she's always. Right, I got you. They gave me this electric graphic, I'm adding like Cal China.
Yeah.
That's all I was at.
You're lucky too.
I had to get the color correct.
You're gonna say something. I like that.
Yeah, so.
Yeah. I'll export it.
Okay, sounds good.
I got you running crazy.
Uh,
I was gonna ask you. I saw that. Never mind, I guess.
Are you serving high or are you serving off or?
So it already begins.
When you did, yeah, I'll let you know. It's like, right. I'm up to try to feel, then I'm up to do.
Those are words. What's that? Why you trying to go Peter? Nate's a better move than you, right?
I'm in the greatest.
I'm so happy.
Yeah, don't have anything.
That's been the greatest plus one.
He hasn't lost his water.
Yeah.
Don't be having close like 2 minutes. Yeah, no.
It's to get breath loss.
We should take your butt now, right? You should chair.
There you
No.
go.
No.
It's kind of fun. Witless.
Yeah. So.
Are they having
Yeah.
No, see, the people who already
Oh.
yeah, so how would you know that it's like,
Yeah. Wait.
And just talking about.
I just showed Mark. I was like, oh, interesting, so I didn't know. My bad, bro. Yeah, like, you know.
This is, because I think on Sunday night,
Oh, yeah, I'm sorry, yes.
Finally got the full sim going.
Got it?
Finally.
Nice.
Yeah, we got our CO and CD numbers.
Yeah.
The only thing is, I'm having trouble with the stream tracers in Caribbean.
Okay. That's an easy
But
fix.
that's an easy fix.
Yeah,
Like, we
yeah.
have. Sorry. I want to. Yeah, I was running. I had like I think I did like 3 or 4 iterations this week. It was running
Okay.
for like total of like 9-ish hours.
Okay.
So
Not bad. Okay, that's good. Yeah, we can go over the results in office hours if you want.
yeah, like our target CO was like almost exact.
Gotcha. Well, let's talk after because
Yeah.
all right, guys, it's 4 o'clock. Let's go and get started. How's everyone doing today? Good, good. Thanks for asking. I'm good. I had kind of a rough weekend. I got sick, but I think more consequentially, I forgot 2 very important things that any guy should never forget. I forgot my mom's birthday on Friday. Well, I knew where it was, but then I forgot to text my mom. So then I called my dad, and I could have played this off, and he gave me an out to do this, but because I was on the phone with my son, and then my dad was like, "Oh, Isaac, I want you to say happy birthday to grandma." And I gave the most audible, like, "Oh, I forgot." I should have just played it off and not done that. So that was strike number 1. And I forgot today is my wedding anniversary with my wife. But to be fair, my wife also forgot. It's like oh. So yeah, not the best sequence of events for me, but you know, but I chalk it up to just lack of sleep because of a newborn son. So, and I was forgiven. I think we'll see. Okay. Anyway, back to CFD. So plan for today is we are going to be continuing our example from last time. I know we didn't end the example in the best of places last time. We kind of stopped right before we kind of got to the climax, but you know we'll finish that up today. Other announcements I want to make is that homework 1 was posted. So homework 1 should not take you guys too long. It's mostly just on diffusion with finite difference stuff, and so actually after today you should be able to do the homework. So it is due next Wednesday. I think I set the due date for. And so, you know, you guys can go ahead and start working on that. The other thing I posted on Canvas on Friday was I posted just a survey. So I'm working on the open foam stuff for the second half of the class, and I'm trying to think of kind of the best way to deliver that to you guys, or the best way to teach you guys. So one option is just to have you guys just run OpenFOAM locally on your own machines. So that's why I kind of sent that survey out there. So I can get OpenFOAM to work on Windows, no problem. I have a Windows machine myself, and so I feel pretty confident I can help you guys out with that. OpenFOAM does run on Mac, although the installation and running OpenFOAM on Mac is a little bit different. And so, you know, that's why I'm trying to get a gauge to see how many people are using Macs. The other option that we have, and I'm kind of leaning towards this now, is to actually get you guys set up on a supercomputer, and to have you guys run the simulations there. It'll be a little bit more work to get it set up, but I think that will be the cooler thing. And we can run a lot more sophisticated simulations on the cluster more than just your own personal laptops. And so, but I at least wanted to get a gauge in terms of how people are running, or what computers they're using for their schoolwork. Just so that, you know, we can kind of make the most informed decision. We may go both, you know, I may teach you guys how to use it on your own laptop, and I'll teach you guys how to get set up on a cluster too, just so you have kind of both skills from this class. Okay. So that survey is due this Wednesday. It's just literally just 1 question, and so it shouldn't take you guys too long. So, and there are points attached to it. So there are 10 homework points attached to that survey. So please make sure you do that before the Wednesday deadline. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So we're in the middle of doing 1D diffusion. With finite differences. Okay. So over the past couple of lectures, we've introduced this idea of finite differences as a way to approximate derivatives with an algebraic expression. And so we're first going to be applying this this idea to diffusion equations. And diffusion equations are basically just second order differential equations. So we have a derivative here. So d squared phi dx squared is equal to 6x, right? So this was specifically the example that we were doing, although we can apply finite differences to any differential equation, okay? And so what we did was we basically took this derivative and we replaced it with its finite difference approximation. And so its finite difference approximation is phi I plus 1 minus 2 phi I plus phi I minus 1, all divided by delta x squared, okay? And then just inherently, we've also discretized the right-hand side by 6x. Okay. All right. And so by doing this, and then applying this equation to a discretized grid, okay? And so by grid, basically what I mean is you take your domain, right? We're sticking with 1D for now, but in a week or so, we'll move on to 2D, right? A grid basically means that you take your continuous domain and you break it up into a discrete number of nodes in this case, okay? Right? So basically for the example that we were doing, we have 5 nodes in our system, right? So node 0, 1, 2, 3, 4. Okay. All right. So I chose 5 nodes just because that's kind of the easiest to kind of do in a classroom example. But you'll see on your homework, you're going to actually do the same thing, but for different numbers of grid nodes. Okay, and then you're gonna compare and see what you get from the results, right? Okay. So by applying this by applying this finite difference equation to each of these nodes, the idea is to get an algebraic equation for basically for each node where this is applied to. Okay? Right? And so if we apply this finite difference equation to our 5 nodes, then we should get 5 equations. Okay. Okay. And so what we saw, right, when we applied this finite difference equation to the 5 nodes, we did get 5 equations, but 2 of those equations were not usable, mostly just because we're only limited to the nodes, or we're only limited to just functions of our solution within our domain. Okay. So when we applied this finite difference equation to all the interior nodes, and so node 1, node 2, node 3, right? These are okay because these are all interior nodes. Okay. And so interior nodes have the nice property where they have neighbors on both sides. Because if you look at our finite difference approximation here, right? So we have phi I plus 1 minus 2 phi I plus phi I minus 1, right? And so in order to apply that equation, we need to have a neighbor to the right. That's phi I plus 1. and we need to have a neighbor to the left, so that's phi minus, okay? That's only true for the interior nodes. And so if you look at the boundary nodes, right? And so let's say we look at node 0 and node 4, right? Right. These nodes are sitting on the boundary, so they only have one neighbor, right? So in the case for node 0, there's only a neighbor on the right, and then for node number 4, there's only a neighbor on the left. So that means for our boundary nodes, we can't directly apply our finite difference equation to those nodes and get an equation that we can solve. Because we're going to get, by applying our equation at those nodes, then, we get values of phi that we can't solve for because they don't exist. Okay. So for these boundary nodes, we need to do something a little bit different. We still need an algebraic equation to solve for their values. It's just how we obtain that algebraic equation is going to be a different way than just applying our finite difference. And so the way that we're going to obtain the algebraic equations for those boundary nodes is to use our boundary conditions. Okay. Right. So it makes sense. So for the boundary nodes, we need boundary conditions. And those boundary conditions, they're going to replace our finite difference equations for those nodes. And they're only going to involve that. Okay. Okay, so that's where we're at. So I believe we did the finite. I believe we did the boundary equation for node 0 for this example. But we'll kind of just review everything just so it's I think it's better to see it as a whole package. Okay. But that was just kind of a recap of how we got here from last time. Are there any questions on any of this? Yes.
The last example you gave us of boundary conditions, they're ever going to be a case where we actually find the boundary condition?
That's a great question. So the boundary conditions usually are a reflection of the realistic scenario that you're trying to simulate. And so usually you set the boundary conditions to best emulate your conditions in real life. So for the purpose of this class, these are all kind of more or less contrived math problems. It's going to be a while before we actually do the realistic flow simulations. So for now, I'm going to give you guys the boundary conditions for every problem. But when we start to get to the second half with OpenFOAM, you guys are doing your own simulation, your own projects. A big part of CFD is determining what boundary conditions you need to use to best emulate those types of physical phenomenon. And we'll cross that bridge when we get there. So, yeah. All right. Any other questions on this? Okay. All right. So let's talk boundary equations. Okay. So let's first kind of remind ourselves that there are typically two types of boundary conditions that you can have in a generic kind of boundary value problem like this with a differential equation. The first type of boundary condition is known as a Dirichlet boundary condition. Okay. So a Dirichlet boundary condition, in those types of boundary conditions, we are directly going to specify the value of the solution at the boundary. Okay. So in those cases, or in this sense, Dirichlet boundary conditions are very straightforward. Just because it just defines kind of what the solution has to be. Okay. So some common Dirichlet boundary conditions that you'll see in CFD. Probably the most common one that you'll see is called the no-slip boundary condition. So in the no-slip boundary condition, we're basically saying that any fluid that's in contact with this surface or with this wall is going to have a velocity of 0. Okay. And so remember in CFD, velocity is the primary variable that we're solving for. So any type of boundary condition that specifies the value of velocity, that's going to be a Dirichlet boundary condition. Okay? So no slip is very common. Another very common one is if you're going to specify a certain flow rate or certain velocity, right? So that's very common in internal flows. So if you're going to be simulating pipe flow of some kind, oftentimes you're going to specify how much fluid or how much water is going to be passing into your domain at that boundary. And so that's also a Dirichlet boundary. Okay. All right. So in the example that we were doing, we did have one Dirichlet boundary condition. Okay. There's an example. Right. So the boundary condition at x is equal to 0 in our example was a Dirichlet boundary condition. Okay. So the way you know this is a Dirichlet boundary condition is that if you look and see what's on the left-hand side, you see that we have phi here, okay? Right. So what this boundary condition is saying is that the solution value at x is equal to 0, we're going to directly specify what that is. All right, and I believe we kind of went over this last time. So we saw that x is equal to 0 coincides with the node 0, right? So if we go back up to our domain here, node 0, this is at x is equal to 0, okay? And so what this boundary condition is saying is that phi 0 is equal to 1, okay? So that right there is our boundary equation. And the reason we're doing that is that phi 0 or node 0 coincides with boundary at x is equal to 0. Okay. Okay. So Dirichlet boundary conditions, usually are fairly straightforward, in the sense that, we can form their equations pretty easily. But I'm going to do something that's might be a little bit strange with this equation. I'm going to expand it, okay? And I'm going to expand this equation to include all the other nodal values in the system, okay? Within that equation. Right. So this is going to look strange. This is going to look strange at first. I know we're taking a very simple equation here and we're going to make it complex for seemingly no reason. But you're going to see that there is going to be a very important reason for this once we get to the linear system. Okay. Okay. So what are all the nodal values? So all the nodal values, what I mean by that is basically the values of phi at every single node in our grid. Okay. So in our situation here, we have 5 nodes, right? Phi 0, phi 1, phi 2, phi 3, phi 4, right? Right. So that equation there has all of our nodal values, okay? But in order to make this equation consistent with our boundary equation, we need to add coefficients in front of all of these phi values. Okay. All right. So for example, I'm going to take the number 1. I'm going to multiply that by phi 0 because that's consistent with the previous equation. And for all the other phi values, because they are not present in this equation, I'm going to multiply them by 0. Okay. So we have 1 times phi 0 plus 0 times phi 1 plus 0 times phi 2 plus 0 times phi 3 plus 0 times phi 4 is equal to 1. Okay. So this equation, if you actually simplified it and actually, crossed out the terms that multiply by 0, is equivalent to the equation above. Okay. All right, so why would we do this? Why would we go through the trouble of expanding such a simple equation and turning it into something more complex? Well, eventually what we're going to do is we're going to take our linear system here, we're going to take our system of 5 equations and 5 unknowns, and we're going to put it in matrix form, okay? Because that's kind of how we input these systems into computer programs to solve. And so to do that, we need to have an even square matrix, 5 rows, 5 columns. And so we need to know what entries to put on each column. Okay. And so we're actually going to do this for every other equation. But I'm not going to be as explicit as this, but this is, when you see zeros in our final linear system, this is kind of what they represent. All right. Any questions on this so far? Okay, good. All right, so that's the first type of boundary condition, which are Dirichlet boundary conditions. So those are pretty straightforward. Okay. The other type of boundary condition that you'll see is what we call a Neumann boundary condition. Okay. Now, Neumann boundary conditions are, I would say, a lot more versatile. So, you'll see Neumann boundary conditions used to represent lots of different things. But at its core, at least mathematically, a Neumann boundary condition is a basically condition on the derivative of the solution. Okay. So some common Neumann boundary conditions that you'll see in CFD, probably the most common one that you'll see is some kind of pressure boundary condition. And that always trips people up because, technically pressure is a primary variable. It is something that we're going to be solving for in the CFD. So it's kind of strange to say that pressure is a Neumann boundary condition versus a Dirichlet boundary condition. But traditionally, velocity is really kind of the main variable that we're solving for. And the way that pressure boundary conditions are often specified, at least in code, is they specify it as like a stress term, which is a derivative of velocity. Okay. So pressure boundary condition is probably the most common. Sometimes you also see some shear stress boundary conditions that are applied. Sometimes you'll see stress-free boundary conditions, but anything involving kind of a pressure or a stress, those are usually Neumann boundary conditions in CFD. Okay. All right. So now in our example, right, we had a Neumann boundary condition, and it was on the other side of the domain. So we said that d phi dx at x is equal to 1 is equal to 0. Okay. Right. So this was the Neumann boundary condition on our example problem that we went over. Okay. Sorry, this is not something I made up now. This was the problem that we were working with since last. Okay. So for Neumann type boundary conditions, once again, we do need to turn this into an algebraic expression, but it's not as straightforward as Dirichlet in the sense that, we can't just directly specify the phi. Okay. But, if you look at our Neumann boundary condition, we have a derivative. In this case, it's a first order derivative. We already have a tool to transform derivatives into algebraic expressions, which is finite differences. Now, it's not going to be the same finite difference scheme we used for the governing equation, right? So our governing differential equation had a second order derivative. So in this case, we're only going to apply a finite difference scheme for a first order derivative, okay? But we need to be careful about the scheme that we used, right? So remember, for first order derivatives, we had three different options that we could choose, right? So we had our central difference. We had our forward difference. And we had our backwards difference. Okay. Now, at the time, it seemed like central difference was the only scheme that we should use because it was the most accurate, right? But let's think about this specific use here, and let's see kind of what the best option for the difference should be. Okay. Okay, because remember, we're applying this finite difference at the boundary, right? So if we look at our domain again, right? Right, 0, 1, 2, 3, 4. Okay. We're applying this scheme on the right-hand boundary right here, right? For node number 4. That's where this northern boundary condition is being applied, right? For node number 4 here, we only have a neighbor to our left. We don't have any neighbor to the right because that's the end of our domain, right? And so that should kind of tell you what type of scheme that we should use. So, we should not use a scheme that uses any kind of neighbor to the right, right? So let me write out these three schemes for you just so that you can kind of see what they look like, right? So for central difference, remember, we have phi plus 1 minus phi minus 1, all divided by 2 delta x. For forward difference, we have phi plus 1 minus phi, all divided by delta x. And then for backward difference, we have phi minus phi minus 1, all divided by delta x. Okay. All right, so any scheme here that relies on getting the value of phi on the right neighbor is not going to be viable here just because we don't have a right neighbor. We're at the boundary, right? And so, central difference, that relies on phi plus 1, so we cannot use that. Forward difference also depends on phi plus 1, so we cannot use that. And so that means our only option for, for the finite difference scheme here is going to be backward difference, because that only depends on the value of the node itself and its left neighbor, phi minus 1. Okay, so let's go ahead and apply that. So we have phi minus phi minus 1, all divided by delta x. And in this case, the value of that derivative is 0, right? But that's not always going to be the case. Sometimes you might have a right-hand side there that's going to be active. But for this specific case, the Neumann boundary condition is equal to 0. Okay. All right. So let's go ahead and simplify this. And so, let's go ahead and we can multiply both sides by delta x. That's going to get rid of that denominator because the right-hand side is 0, right? And then we are applying this at node number 4. So that means we're going to set I is equal to 4, excuse me. All right, so I'm going to get rid of this delta x. And then we're going to set I is equal to 4 for the boundary node. And so what we get is an equation, phi4 minus phi3 is equal to 0. Okay. Or in other words, if we wanted to put it in terms of all the other nodal values and we wanted to put them in order, it would look something like this, right? So we have phi 0, 0 times that, plus 0 times phi 1, plus 0 times phi 2, minus 1 times phi 3, plus 1 times phi 4 is equal to 0. All right, good. All right, and so with that, we have everything that we need. So we have our 5 equations that we need to solve for phi 0 through phi 4. Okay. Now, we're not actually going to be solving it by hand. We're going to set up the equations, and then we're going to use MATLAB to solve for the values for us. Okay. All right, so let's do this. So I'm going to write down our 5 equations just one more time, just so that they're all kind of in one nice place, and then we'll switch over to MATLAB just to kind of show you how to solve. Okay, but before we kind of jump into that, just because it's a lot of writing at that point, are there any questions on the Neumann boundary condition? Yes.
Why did we use the backward difference? Just because it's all the way on the right hand side, right?
Exactly right. So if you look at the forward difference and the central difference, they both rely on phi I plus 1. But if we're applying this on node 4, there is no I plus 1 because I plus 1 kind of is over the edge of the domain. And so we could only use phi I and phi I minus 1.
So if we had node 0, a question, we would use forward difference.
Exactly right. So in that situation where your Neumann boundary condition is on the left-hand side of the domain, then you would use forward difference because node 0 has the opposite problem. Node 0 has a neighbor to the right, but no neighbor to the left. And so in that case, you would have phi I plus 1, but not phi I minus 1.
Okay. Thank you.
Okay, all right, so let's write out our 5 equations. All right, so I'm going to organize our 5 equations based on the 5 nodes that we have. So node 0, 1, 2, 3, and 4. Okay. All right, so node 0, remember this was our Dirichlet boundary condition. So this was 1 times phi 0 plus 0 times phi 1 plus 0 times phi 2 plus 0 times phi 3 plus 0 times phi 4 is equal to 1. Okay. Right. And then just because we have it right above there, let's go ahead and write out the last equation, which is our Neumann boundary condition. Okay. So it's 0 times phi 0 plus 0 times phi 1 plus 0 times phi 2 minus 1 times phi 3 plus 1 times phi 4 is equal to 0. Okay. You don't always have to write in all the zeros here. I'm just doing it just for illustrative purposes right now, just because we're going to turn this into matrix form. So when you're doing your homework, feel free to just write phi 0 is equal to 1, or on the last equation, just write phi 4 minus phi 3 is equal to 0. I'm only doing this here just to kind of show you where these coefficients come from. Okay. All right, and then we have our interior node equations here. Okay. Okay, so for node number 1, we have 1 times phi 0 minus 2 times phi 1 plus 1 times phi 2 plus 0 times phi 3 plus 0 times phi 4. Okay. All right, and then we have the right-hand side of the equation. So remember, all of our interior equations are based on our original differential equation, which in this case was d squared phi dx squared is equal to 6x, right? And so we have 6 times x. So in this case, it's x1. So x, remember, is the x value of the first of node 1, okay? Multiplied by delta x squared, okay? All right, and then we're going to do the same thing for the other 2 interior nodes. So I'm just going to go quickly here. You know, it's a little bit of a mess. I kind of regret this a little bit, but hopefully, you know, when we put the linear system, you know, these coefficients are just going to slide right into there. Okay. But I wanted to show you this first, just so that I think, you know, first time you kind of see a huge kind of system of equations like this, and you see it transform to the coefficients. You know, a lot of times people ask, you know, where did you get that zero? How did that equation become that row? And so, you know, hopefully with this, it becomes a little bit more straightforward. Okay. Okay. All right. So let's take this equation and then let's put it in matrix form. So to put it in matrix form on the left-hand side, I'm just going to extract out the coefficients. And so everything that's in front of the phi's, we're going to put that into a matrix. And then we're going to multiply that by a vector of our solution values, phi1 or phi0 to phi4. And on the right-hand side, we have everything on the right-hand side. Okay. Okay. Let's go ahead and transform this matrix form. Okay. And so we need a 5 by 5 matrix on the left-hand side here. And so that's going to be multiplied by phi0, phi1, phi2, phi3, phi4. Okay. Okay, so let's go ahead and fill in the coefficients according to our linear system here. So the first row of this linear system is going to be our Dirichlet boundary condition. And so if we just read off the coefficients, this is going to be 1, 0, 0, 0, 0. Okay, good. All right, second row in the matrix, is going to be our equation associated with node 1. So that is one of our interior nodes. And so we have our second order finite difference approximation. So that's 1 minus 2, 1, 0, 0. Okay. Well, let me write in the right-hand side. So the right-hand side, it's just going to be the values there. So that's going to be 1 for second row. That's going to be 6 times x1 times delta x squared. Okay. Third row in the matrix is going to be our equation associated with node number 2. And so that's going to be 0, 1, minus 2, 1, 0. And then right-hand side is going to be 6 times x2 times delta x squared. Okay. All right, and then fourth row in the matrix is going to be our equation associated with node 3. And so this is going to be 0, 0, 1, minus 2, 1. Right-hand side is 6 times x3 times delta x squared. Okay. And then last row in the matrix, that is the equation associated with node 4, which remember is our Neumann boundary condition. So that's 0, 0, 0, minus 1, 1. And then right-hand side for that Neumann boundary condition is. Okay. And so what we have here is a matrix, the matrix form of a set of linear equations. And so, you know, we can use this to solve for phi0, phi1, phi2, phi3, phi4. Okay. Now, you know, an equation, a system like this, 5 by 5, you know, probably is not the hardest one to solve by hand. So, you know, if you enjoy this kind of thing, feel free to solve it by hand. But I'm going to show you how to solve this in MATLAB just to kind of make things a little bit easier. It is a little bit tedious to have to enter in all of these values. I know that, but then, you know, it is, I think that's probably a little bit easier than trying to solve this by hand. Okay. And if you have a graphing calculator that you can use to solve this and you feel comfortable doing that, definitely you can do that too. And so I'm only showing you the MATLAB way just because, you know, I think everyone here has access to MATLAB. But if you prefer to do this in a graphing calculator, that's fine with me too. Okay. And this is going to be the extent of the MATLAB that I expect from you guys. You know, so you know, we're not actually programming in MATLAB. We're just using it as a glorified calculator. Okay. All right. Any questions on this before we jump into the MATLAB? Okay. All right. So let me go ahead and switch over here. Right. So hopefully everyone has this matrix down because, you know, we are going to reference it. Okay. All right, so we are in MATLAB now. Okay. All right, so I'm going to go ahead and define a new script. You don't have to do a script. You can just do it straight from the console here if you're comfortable. But just for longevity purposes, in case you need to reference this later, I always like to save it as a script. Okay. Okay, so let me go ahead and save this. So let's save it EGME 436, February 2nd, my wedding anniversary, so I'll never forget. And this is just me, but whenever I write a MATLAB script, I always start with clear all, close all, CLC at the top. All that does is it just clears all the variables and just make sure you're starting fresh. Okay. Okay. All right. So in order to use MATLAB to solve a linear system, essentially we need to define a matrix to represent our left-hand side. Okay. So we need to basically define a left-hand side matrix variable. Right, so we'll do that in a second. And then we also need to define a right-hand side vector, okay? So those are the two things that we needed in our problem, right? So let's start with the left-hand side matrix, just because that one is fairly straightforward, okay? So there's lots of ways to build a matrix in MATLAB. I'm going to show you kind of the way to just directly specify, which I think kind of works well for our purposes here in this class. But feel free to use whatever method I think you feel most comfortable, okay? Okay, so to specify a matrix this way, we're basically going to construct the matrix row by row, okay? Right, and so we're going to start at the top and then, add rows to the bottom here, okay? So from our example here, the first row in the matrix is 1, 0, 0, 0, 0. So the way we specify that in MATLAB is we do 1. Oh, question, yes. Yeah.
Able to zoom in.
Oh, yes, thank you. Yeah, I always forget to do that. Let's make the font size a little bigger. Once. Okay, better. Okay. Okay, so let's specify that first row in the matrix. So the way to do that is we're going to separate each entry in the row by a comma. And so we're going to do 1, 0, 0, 0, 0. Okay. All right, so that's the first row in the matrix. When you're done modifying a row, in order to go to the next row, you're going to need to use a semicolon. Okay. So that semicolon at the end there tells MATLAB, we're done with this first row. Let's go ahead and specify the next one. Okay. Now, technically, you can start inputting the entries in the next row here. So you can do 1, -2, 1, 0, 0. Okay. And you can just keep doing that. And so you can basically define it all on one line. But just for the sake of readability and sanity, what I like to do is I like to actually separate the rows in the matrix by separate rows in the code. So the way to do that is that after you do the semicolon, you're going to add 3 dots. Okay, so dot, dot, dot. Okay, and then you can actually put this next thing on the next row. Okay. Just to make things a little bit easier to read, because in the homework, I'm basically going to have you guys repeat this problem, but for a 9-node system and then a 13-node system. And so, adding 13 nodes in a row like that is if you make a mistake, it's going to be hard to find. So I like to kind of do it. I like to kind of separate it by row. Okay. Okay. So let's go to the next row. So let's add our dot, dot, dot. Okay. Next row in the matrix is 0, 1, -2, 1, 0. Okay. Semicolon, dot, dot, dot. Next row, 0, 0, 1, -2, 1. Okay. Semicolon, dot, dot, dot. Okay. And then last row in the matrix is going to be 0, 0, 0, -1, 1. Okay. Okay. So that is our left-hand side matrix. That's all the coefficients that we derived, from our. All right. Any questions on that? Okay, now we have our right-hand side vector. So right-hand side vector, this is everything that was on the right-hand side, okay? And to help us out here, I'm gonna go ahead and define some other variables up here. Just to make things a bit more clear, okay? Just because our right-hand side depends on the values of these. So let me define the nodal coordinates first, right? So the x coordinate for node 1, x1 is 0.25. x2 is 0.5, x3 is 0.75. Okay. And remember, this comes from the fact that if we draw our domain here, right? Remember, we had a 5-node domain. So 0, 1, 2, 3, 4, right? So remember, we assume that our nodes are all equally spaced, and so there's no bias in our domain, right? And so that means the value of x at node 0 is 0, right? And then we know that our domain goes from 0 to 1. So we know x4 here has to be 1, right? That means every x value in between is kind of an equal increase to each other. So x2 right in the middle is 0.5, right? x1 is halfway between those two, so x1 has to be 0.25. And then x3 must be 0.75, okay? So those are basically all of the x values for each node in our domain. Okay? And then we can also see from this figure that the spacing in between the nodes, or delta x, is 0.25. Okay. And then our values here depend on that as well. So let me define dx. dx is 0.25. Okay. All right. So again, you don't have to do this. You can just put the values in directly into the matrix, but I just want to kind of make things consistent with what we have in the notes in terms of symbols. Okay. Okay. All right. So let's go ahead and define this this matrix here, or this vector, excuse me. So the first entry in our right-hand side was a 1. Okay. And that was consistent with our Dirichlet boundary condition. Second entry is 6 times x1 times dx times dx. Okay. Next entry is 6 times x2 times dx squared. So we can just do dx times dx. Third entry, or fourth row, excuse me, is 6 times x3 times dx squared. And then our last entry is just 0. Okay. All right. Any questions on this so far? Okay. All right. So last thing. So now that we have our left-hand side matrix and our right-hand side vector, okay. The last thing we're going to do is we're going to invoke kind of a special operator within MATLAB called the backslash. Okay. Okay. So we're going to define a new variable here just to store the solution. Right. So let's call that sol vector. So sol vector stands for solution vector. And this is going to be our left-hand side matrix. Okay. We're going to use the backslash operator. So the backslash is, there's 2 slashes on your keyboard. So there's one that we typically use, which is the divide sign. So that one's to the left of the right shift. But the slash that we actually want to use is the backslash, which is the one that's right above the enter key on your keyboard. Okay. All right, so if you try to use the other slash, then you're going to get an error. All right, so that's it. And so now that we've defined our matrices and vector, we can go ahead and run this and solve. Okay, and that is our solution. And so if you open up the variable here for your solution for sol vector, right? This will kind of give you what the solution is at each node. Okay. So the value for x0 is 1. The value for x1 is 0.4375. The value for x3 or x2, excuse me, is minus 0.0312. Value for x3 is minus 0.3125. Same thing for x4. Okay. Okay, and if you wanted to plot this, and so this is kind of optional. I think in the homeworks I've plotted the solution for you just so that you can see, right? But to plot it, it's actually very simple. So all you have to do is you open up a figure and you just plot just like that. Okay. Okay. And then we wait for MATLAB to produce a plot, right? And then this is the plot of our solution here. So you can see it starts at x is equal, or phi is equal to 1. And then it goes down And then just like our boundary condition says, we have a basically zero derivative on the right-hand side. And so that is our solution. Okay. So what you should see, in the homework, when you redo this problem for different numbers of nodes, right? As you increase the number of nodes, the solution actually gets more and more accurate. All right, but that's kind of a crash course in MATLAB. So, like I said, this is the extent of what we're going to do in MATLAB. We're just using it as a glorified calculator. But it is useful in these cases just so that you can take your linear systems and you can actually get a solution out of it. All right, any questions on this? All right. So that's that example. Okay. All right, so we have time for a couple more points. So actually, let me switch back to our iPad here. Okay. Maximize this again. Okay, so what we just did, this kind of very long, drawn out example that took us all the way from last lecture until now. That's basically how we're going to do things, right? So for the next couple of weeks, we're basically going to be taking differential equations. We're going to be applying finite difference to it. We're going to get a linear system like this, and then we're going to solve for its solution. Usually in MATLAB. So I would never ask you guys to solve a system like this. Okay. Okay. So on Wednesday, my plan is to kind of move on to the next important, behavior in Navier-Stokes, which is convection. But before we move on to convection, there are a few kind of final points, final notes I want to make on this stuff. Just on finite difference schemes in general. Okay. So first kind of topic I wanted to kind of touch on is using different finite difference schemes. Okay. All right. So I kind of hinted at this earlier last week that the schemes that we're going to be using in this class are not the only schemes that are available in finite differences. There are other schemes out there, right? So let's actually use that. Let's use the example of our second order derivative here just to kind of illustrate this thing, right? So in the last example, we use kind of the classical kind of central difference scheme for second order derivatives, which was phi I plus 1 minus 2 phi I plus phi I minus 1, all divided by delta x squared. Okay. And what we said was that this is second order accurate. As in, we expect the error to diminish as we reduce the grid sizing by a factor of squared. Okay. Right. So reducing the grid sizing by half will reduce the error by a factor of 1/4. Okay. Okay. But what if we use a different finite difference scheme, right? So let's use another central difference scheme. Okay. But let's use the next central difference scheme that is more accurate for the second order derivative. Okay. So for example, let's use this one here. So another way to represent the second order derivative would be something like this. So we have minus phi minus 2 plus 16 phi minus 1 minus 30 phi right, plus 16 phi plus 1 minus phi plus 2 all over 12 delta x squared. All right, so this scheme here, this scheme is fourth order accurate. Okay. So that's pretty good, right? But of course, the downside for this scheme is that you do have to bring in, not only your left and right neighbor, but your neighbor's neighbor as well. Right? So that's why we have phi minus 2, phi plus 2. Okay? So instead of only involving 3 nodes, this scheme involves 5 nodes. All right. So of course, that makes sense in some situations, but if we look at our relatively simple problem, right? Where again, we only had 5 nodes in our total system here. Right? Based on kind of what we've seen before, right? We can only use this fourth order scheme if we had neighbors and if our neighbors had neighbors. Okay, so basically, have 2 neighbors to the left, 2 neighbors to the right, right? There's only one node here that we can apply this to, which is node 2, right? Okay. All the other nodes in the system, we don't have enough neighbors in order to apply that scheme. Right? So for a couple of these nodes, that's fine, right? And so if we look at, let's say node 0, node 4, right? Right, we can't apply this scheme to those nodes, obviously, because these are boundary nodes, right? But that's no problem because, for node 0, node 4, we're just going to apply boundary equations here anyway. Okay. But what about nodes 1 and 3, right? So 1 and 3 are technically still interior nodes, and so they don't have they're not on a boundary, and so we can't apply boundary conditions there. Okay. But they don't have enough neighbors to actually apply our fourth order scheme. Right. So these are interior nodes. All right. So what do you need to do in these situations, right? So this is not uncommon. So, for situations where you have to use a higher order scheme, then, for nodes that are, not quite on the boundary, but not interior enough to apply the scheme, it's not uncommon to have to use a different scheme for these types of nodes. Okay. Okay. Now question, yes.
By neighbors, do the neighbors have to be other interior nodes?
They don't have to be. So the neighbors can be boundary nodes too. But for this fourth order scheme, we need two neighbors to the left and 2 neighbors to the right. And so for node 1, we have one neighbor to the left, which is node 0, but we don't have another neighbor beyond that. So we can't compute phi minus 2 because that wouldn't deal with that. Yeah, but the neighbors can be boundary nodes or interior nodes. Okay, so we would have to use a different scheme. So the simplest thing to do is just to kind of go down in order, right? And so we can just use our classical second order scheme. So that's, you know, that's what we did in the previous example, except we kind of applied that classic second order scheme all throughout, right? So the classic second order scheme only requires one neighbor in each direction. And so, so that's one option that you can do, okay? It's not ideal and you're usually not going to see, I would say, you know, practical codes written like this. Because usually, you know, if you're going to go through the trouble of making your equation fourth order or your solution fourth order, you want to apply that fourth order accuracy everywhere. It's kind of weird to have certain zones that are fourth order accurate and then certain zones that are second order accurate, because then, you know, then it kind of calls into question, you know, your overall solution accuracy anyway. So that's kind of the easy solution, but it's not often done because it kind of defeats, it kind of kills your effort anyway. Okay. Another option, okay, which, you know, unfortunately adds even more work, is to use what's called a shifted scheme. Okay. That way you can kind of still maintain your same order of accuracy for all of your interior nodes, and still have the neighbors that you need for, you know, to do the calculation. Okay. Now, what do I mean by shifted fourth order scheme? So, you know, we know that our fourth order scheme, you know, we're probably going to need to involve 5 nodes in our calculation, right? Right. But right now, the way that these 5 nodes are kind of dispersed, right? We have our central node and we have 2 neighbors on the left and right, right? So this is kind of how it is. So we have our central node. We have our neighbor to the right, I plus 1, and we have our neighbor to the left, I plus 2, right? And then the same thing on the left. Right? So this is our centralized stencil. Okay. Where we have to involve 5 nodes, and the 5 nodes are centered on node I, right? Right. But what if we shifted this? And so instead of being centered on our centered node, what if we shifted it to the right, where, you know, we would only have to involve 1 neighbor on the left, but by compromise, we'd have to involve 3 neighbors on the right. Okay. So what if we did this instead? Then we have only I minus 1 here, I plus 1, I plus 2, I plus 3. Okay. So that our finite difference scheme is a little bit more biased on one side versus the other. Okay. So with this scheme right here, we only need 1 neighbor to the left. But 3 neighbors on the right. Okay. Yes.
On the centralized stencil, that first point, how is it I plus 1?
Oh, I'm sorry. That should be I minus 2. Thank you. Yeah, doesn't make sense. It's on the left. It should be minus. Yeah. Okay, so for our shifted stencil, you know, we need 3 neighbors on the right, which is a pretty tall order. But there is a node here that does fit that criteria, right? So if we go back to our domain here, right? And let's look at node number 1, right? So node number 1 is in kind of the unique position where it has 1 neighbor on the left, but it also has 3 neighbors on the right. So we can actually apply this shifted scheme to node 1. Okay. Right. Now, for the shifted scheme, you know, you have to be careful because it does change the values of the coefficients. And so you'd have to kind of look up. And, you know, the good thing is that, you know, finite difference schemes are very well studied at this point. So you can definitely, you know, there was a Wikipedia page on it last time I checked. So you'd have to look up, you know, what the coefficients are for that. And you'd have to adjust your code to look for that exact situation where you have 1 neighbor on the left, 3 on the right. So it is very cumbersome to implement. but you can do it, okay? And then you can do the same thing, so you come up with another scheme for node number 3, right? So node number 3 has a unique property where it has one neighbor on the right, but 3 neighbors on the left. And so you'd have to come up with another shifted scheme for that, okay? Okay, but theoretically, it is possible to do this, right? And if you're going to go through the trouble of making your code 4th order, then you might as well just go all the way, right? And so you have all these shifted schemes, okay? But that, hopefully should also illustrate to you, why, second order is usually ideal, because that's kind of the most straightforward to implement in terms of code. It's the most straightforward to kind of, understand, because you often don't need more than one neighbor. And second order accuracy is already pretty good. It's usually not worth it to go 4th order or more. But, I did want to kind of talk about this. Not that we're going to do anything with this. We're not going to be implementing any 4th order schemes. I don't even know if OpenFOAM can even get up to 4th order accurate. But I did want to kind of just discuss this briefly, just to kind of show you just how cumbersome it is to go beyond second order accuracy. All right. Any questions on this? Yes.
Is it better to just, let's say, instead of avoiding using that mixed scheme method, is it better to just, for more accuracy, just use second order from the start?
So what second?
Is it better to use second order from the start?
Yes.
As opposed to a mixed method?
Yeah. So typically the way that people achieve better accuracy, just because if you are going to change the order, you have to rewrite your code, which some people are into, 99% of people are not. And so the way to achieve better accuracy for most people is just to refine your grid. Right. So even with second order accurate, we know that our accuracy improves with delta x squared, right? And so, probably the easiest way to improve your accuracy is just to make delta x small. So that means your grid is going to be bigger, your mesh is going to be bigger, which of course increases your computational costs. But that's usually a cost that people are willing to pay. So if you're going to go up in order, probably your simulation would run a little bit faster just because your grid is not going to be as high. But reprogramming your code is a huge cost. But if you do go through that trouble, then you do have a code that works really, really well. It's just that most people are not going to. Okay, so last thing I want to talk about, before we head out for today, is a little bit on errors. Okay, so recall, when you make a finite difference approximation, it's at the end of the day just an approximation. And the differential equations that we saw with finite differences are also just going to be approximate solutions. Okay. Right, and this goes for any computational simulation, whether you're doing finite difference, finite volume, finite element, right? There's always going to be errors, and in fact, there's always an expectation that there are going to be errors in whatever solution that you produce. Okay. All right, so I've been kind of throwing this term error around, but let's actually define it kind of let's define it a bit more precisely here. So when I say error, right, the error basically is basically the difference between what we compute in our finite difference solution, so that's our finite difference computation. Okay. Minus the actual value, right? So this is different ways to say this, but we can say exact solution. Okay. Right, so some people take an absolute value here. In fact, that's usually pretty smart, or they just square the error just to make sure it's always positive. Because sometimes your finite difference computation is going to underestimate, sometimes it's going to overestimate, depending on the situation. Okay. Okay. So for simple problems, we can compute this exactly, right? Because for simple problems, we're able to obtain the exact solution. Okay. Okay. In fact, for the example that we did earlier today, we found the exact solution to that problem in the lecture last time. So actually, one thing you can do, I'm not making you guys do this on the homework, but one thing you can do is you can compare your finite difference answers to the exact solution and compute the exact errors at every single point. Okay. So that's pretty straightforward definition of error. The only issue is that for more complex problems, and 99% of problems that we're going to do with CFD fall into this category, finding the exact solution is not exactly attainable. Okay. So, it's a little bit of a catch-22. So, whenever you run a CFD or whenever you run a simulation, you always expect there to be errors, but you don't know exactly what the error is because you're running a simulation, right? And the reason you're running a simulation is that you can't really measure this in reality, or you don't want to for whatever reason. Usually it's cost, right? So how do we get a sense of the error, if we don't know what the exact solution is, right? Right. In some situations you can, but there are the error does behave in a certain way where we kind of expect the errors to be higher in some places than others. Right. And then I'm gonna center this discussion around the boundary conditions. So, generally around the Dirichlet boundary conditions, we expect the errors to be minimum, if not exactly zero. Because remember, for Dirichlet boundary conditions, we are directly specifying the solution values, right? And oftentimes the direct specification is, something that we know exactly, right? So, think of the example I said earlier where, the most common Dirichlet boundary condition is no slip, right? So no slip is pretty much verified. That does happen in reality. So if you're running a CFD, generally you expect the errors to be lowest around your no slip boundary conditions, just because, we know that exactly. Okay. On the other hand, we expect the errors to be maximized or greater in the ballpark of the Neumann boundary conditions. Okay. So since Neumann boundary conditions is a boundary condition on the derivative, it's not as strong of a specification. It's not as strong of a boundary condition as Dirichlet. And so you expect the errors to be a little bit higher there as well. Okay. And so you should see this very clearly. So when you do homework problem 2 on the homework, right, you should see that, in the Dirichlet boundary condition, no matter how many nodes you have, the solution is always going to start from the same place. But from the Neumann boundary condition, that's where you're going to see kind of the biggest difference in the solution. Okay. Okay, so there's a lot more to say about errors, but I think, we'll kind of save that discussion from when we get to CFD to more practical stuff. But I think this is kind of good enough just to do your first homework. Right? Any final questions before we wrap it up for today? Okay, all right, so that's all we got time for. So thank you guys for coming today. When we come back on Wednesday, we will start to talk about convection and kind of how those problems go. And then, yeah, we'll go from there. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you all on Wednesday.
Get rid of the.
Oh, we just multiplied it on both sides, and so just it's 0 here. Just making it simpler because we're gonna put this into the matrix eventually. You could have the delta X there, but then you kind of more division for you to do.
Because the only cloud.
Sure.
It's obvious. This is just regarding, so. 1, 2, 3 total.
Okay.
Last semester.
Okay.
So I only need one more, which is this one.
Yeah.
So I'm taking it, then I'm really enjoying it.
Don't worry about me, bro.
Good job.
Yeah. Yeah, just check on your CDA, just make sure that you have the 3.
Tomorrow.
I mean, I did
tomorrow.
3, but then.
Yeah,
Just go for it. Yeah.
Okay.
Nate,
You in here, bro.
Nate, you guys are playing tomorrow?
You would expect the error to and then
Yes.
expect to talk about that in the too.
Yeah.
But
So I
so I did the thing, the equation that wrote the boundary tests with the given.
Against Chelsea.
So would the error not be the smallest where?
We're gonna stream the meeting with-
The leading error factor.
So for this, I'm talking just within one
It
semester.
doesn't matter who has
And so if you compare the results between different meshes, then of course the one with the higher number of nodes, that one's gonna be the most accurate.
So your error is gonna be the difference between the numbers is
Good night.
the smallest.
Exactly. Yeah.
Okay.
Yeah. But if you just look at, just the simulation for the 13 nodes, then, and I probably should have had you guys do this, but, if we plot the exact solution is gonna look most like the.
Mm-hmm.
And so, the error are gonna be maximized here. So if you plot the exact solution, it actually kind of goes.
Because at this point, it just kind of goes as a straight line.
Exactly. Yeah. So the real solution is actually down here.
Mm.
And so, if you compare this end to the other end,
Mhm.
then the errors are maximized on this.
Okay, okay, cool, thank you.
Hey, Ahmed, how's it going? Good, good.